This presentation is on calculating and interpreting the two-cell chi-square statistic. This is a highly useful statistic as it's relatively easy to comprehend. The formula is pretty basic and the test is versatile, like the ANOVA and the independent samples t-test. The chi-square statistic was invented by the British statistician Karl Pearson, who also developed the standard deviation. Pearson developed the chi-square especially for nominal level data. Recall what nominal level variables look like. They take on two values, ones and zeros, depending upon whether or not the condition is present. For instance, a registered Democrat scores a 1 for a variable called registered Democrat, while a citizen who is not a registered Democrat scores 0. The problem with analyzing nominal level data is that the mean values and the variances are less illuminating. The mean values, by definition, have to be between 0 and 1, but it's hard to tell what a mean value of, for instance, 0.72 means, other than there are more ones than zeros. In fact, the most appropriate measure of central tendency for nominal level data is the mode. Chi-square, abbreviated as the Greek letter chi squared, is appropriate for comparing frequencies of variable results. The basic chi-square calculation is the sum of the observed frequency minus the expected frequency squared divided by the expected frequency. The observed frequency is what the frequency count is for a variable. The expected frequency is what we would predict the frequency count to be if there were no difference between the two possible values for the variable. Making that calculation for each observed and corresponding expected frequency and summing up the results of those calculations yields the chi-square result. And as with the f-test, there is a critical value for chi-squared, above which the difference between the expected and observed frequency is so large that there must be a statistically significant difference between the observed and expected frequencies. These critical values are displayed on the chi-square table at the 0.05 level of significance on page 168 of the Pollack I book. As a hint, though, we will be using only one critical value, 3.841. The usual rule applies. If the chi-square value at the appropriate degrees of freedom is equal to or above the critical value listed on the table, then you will reject the null hypothesis that there is no statistically significant difference between the observed frequency and the expected frequency. Let's go through an example. Let's imagine that two candidates, Smith and Jones, are running for election, and a sample of likely voters has been asked their views of the two candidates. The results of the 200 voter sample are as follows. The first cell is for Smith, and the second cell is for Jones. Smith receives 110 votes of support. Jones receives 90 votes of support. We want to know if this sample is statistically different from a dead heat between Smith and Jones. What would the null hypothesis be, expressed in percentage terms? 50% to 50%. Thus, the sample would be split evenly, 100 votes for Smith, 100 votes for Jones. In order to figure out if 55% is statistically different from 50%, we'll perform the following operation. Again, the formula for chi-square is the sum of the observed frequency minus the expected frequency squared divided by expected frequency. 110 minus 100 squared divided by 100 represents the cell for Smith, 90 minus 100 squared divided by 100 represents the cell for Jones. And we complete the arithmetic operation. 10 squared and minus 10 squared are both 100. 100 divided by 100 is 1. 1 plus 1 is 2. The chi-square result is thus 2. One rule of thumb for chi-square: it can never be less than 0, since we're squaring the observed frequency minus the expected frequency. We find the degrees of freedom by subtracting 1 from the number of categories. Thus, 2 minus 1 is 1. Next, we need to turn to the table of critical values for the chi-square test in the Pollack 1 book on page 168. Yet, unlike with the other statistical tests we have conducted this semester, we won't need this table for our chi-square tests in order to figure out the critical value at which we decide to accept or reject the null hypothesis. This is because the degrees of freedom for all the chi-square tests we will conduct in this course will all be the same. df equals 1. We will use the 0.05 area to the right of critical value as the correct column, and the critical value we will always use is 3.841. This you can memorize if you wish. 3.841. 3.841. If the calculated chi-square is less than 3.841, we accept the null hypothesis. If the calculated value is equal to or greater than the critical value, then we reject the null hypothesis. Since 2 is less than 3.841, we accept the null hypothesis and conclude that the observed frequency of support for Smith is not statistically different from the observed frequency of support for Jones. We will find that our results for the chi-square test are highly dependent on the size of the sample. Let's change our example around a little bit to demonstrate this. Let's keep the percentage of support for Smith and Jones the same as before. 55% supporting Smith, 45% supporting Jones in the pre-election survey. However, we will change the sample size from 200 to 1,000. Let's see what happens. Smith receives 550 votes, Jones 450 votes. In doing the calculation, 550 minus 500 and 450 minus 500 are 50 and minus 50 respectively. 50 and minus 50 squared equal 2,500. 2,500 divided by 500 is 5. 5 plus 5 yields a chi-square of 10. And with 1 degree of freedom, clearly 10 is larger than 3.841, the critical value. So we reject the null hypothesis now and conclude that there is a statistically significant difference between Smith and Jones. Smith is statistically ahead of Jones. The moral of the story is, the larger the sample size, the better the opportunity to find statistical significance. We conclude this presentation of the two-cell chi-square test.